Record. Is that a toilet flushing?
Yeah.
Did they mute themselves real quick? Oh, it was Noah.
It was Sam.
Oh, was it? We're already recording. So.
Dome Rose with her bat wings.
That was fraught with danger. All right, so let's pick up where we left off with our language. It looks like the last thing we had added in was it if expressions? We have an idea of a Boolean expression. We have an idea of if expressions, and we've tested if expressions. So ask question, test if A is less than 7, and in our environment, A is 6 right now. If A is less than 7, then we want to ask the question. If A is greater than 5, which is, then we should boil down to an 8. See if that's currently the case. Where's my, oh, did we write a print? Maybe that's not, I'm not executing that one right now. Oh no, I'm running the program for this display. So we did a display last time, right? Well, we tried to parse it. We just haven't, we've parsed display. So this creates a print expression list 7. We just haven't put it into our program yet. Got it. All right, so we need to have, do we already have constructors? I assume we have constructors for that guy, because we already have parse expression for it. Well, that's predicates, I don't see it. That's for our, oh, did we not even really start it? Does the parser handle it? Here's my parse expression. I don't see a display in there. Oh, it's called the print expression. Yeah, here's a print expression constructor. Print expression to expression. Print expression. Doesn't look like we've written an extractor. Oh, we have a display expression for, oh, this is for the parser. So my print expression, I have a way to get the expression portion of it out. Okay, so we're going to go ahead and add our print expression, and then we want to move into, in fact, let me talk about what we're going to move into here first. In a language like Java, when we want, and we kind of saw this last time, and I can pretend like it was on purpose, but it wasn't. That one of the weaknesses with Scheme is maintaining state in your program, because you can only do one thing at once, and you kind of have to pass things around, right? When we're in Java and you think about the body of a function or the body of a for loop or something like that, it's pretty common that we want multiple things to happen in a row, right? We kind of have this procedural mindset when we program that, oh, well, I want to do this, and I want to do this, and I want to do this. And our goal isn't always for everything to be all linked together. Sometimes you want to have separate things that kind of occur. And maybe something later in your program is reliant on something earlier in the program, but you might not be ready for that yet. Where Scheme kind of relies on you to say, well, basically, what does Scheme do? Scheme makes it difficult for you to change the state of your variable environment to be used later. You kind of have to pass things around as you go. So if you think about a language like Java, we usually have the, for like an if statement or a for loop. If you think back to when we first learned these things, we would have said that technically the curly braces are not required, right? Because if you have a for loop, for example, and 470 here, yeah. So if we have like a for loop, the syntax for a for loop is, I could say int I is equal to 0, I is less than 100, I plus plus, but then the body of it is some statement, right? So you could write a loop that only does one thing and you don't need curly braces. You can have a single statement, but usually we don't, right? Usually, even if we were going to only have one statement, we still put curly braces, right? Because back then I always said, oh, well, it's never wrong if you use curly braces, right? It's never incorrect if you use curly braces. But because now I can have potentially more than one statement in here, right? I can do 5, 6, 7, whatever things in a row. Where before, if I didn't have the curly braces, the first statement would be part of the loop. The other two would just be sitting out there doing whatever, right? Go back even farther to like a Python, where Python forces indentation and says that anything that's indented under here belongs to it. Things that are not indented under here don't. So the impression would be, well, the implication is that if you have stuff indented underneath an if, or you have something indented underneath a while loop or something like that, that you want all of those things to occur as part of that. So this is where the concept, do you know what it's called? What's an opening and closing curly brace in Java called? What kind of statement is that? We have an if statement, we have a for loop. What kind of statement is the opening and closing curly brace? Yeah, we think of it as like the body of something, right? They're usually called block statements. So a block statement is a collection of, we can technically say 0 or more statements. Because you could have a loop that doesn't have anything in the body, and then Java would probably scream at you and say this doesn't do anything. That actually used to be the way languages worked. I think I probably had shared that example with you, that I had a program years ago on a computer that used to be it's called Double Dragon, that was in the arcades. This was like arcade game in the 80s. And but then we got it for our PC in 1990 maybe, something like that, and it ran fine, like an old 386 DX or SX 25 megahertz computer, like not a fast computer. Fast for that time, but not fast several years later, because that was during the time when computers kept like quintupling in speed every 15 seconds. So years later, my brother and I had tried to put that same software on a much, much faster computer, like a 66 megahertz 486 DX2, whatever, a lot faster computer. And the game was unplayable. Everything was moving too fast because they did everything with busy wait loops. They tried to delay, like when a certain monster comes out, based on how long it took a for loop to go through 1,000,000 times. Well, it took a for loop to go through 1,000,000 times a lot longer on that older computer than it did on this newer computer. So you kind of look at how bad the programming was, when you think about that. So potentially you could have, they were called busy wait loops. We just want to kill some time. Is what we want to do here, and however long this for loop takes to run, not even thinking about that there might be a faster computer soon, because as you got faster and faster computers, even if it didn't become ridiculously faster, the game would become more and more challenging because you'd have less time to. So in the end, we had the entire level of monsters just on top of us, because it also seemed they used busy waits for the guy's movement too. Those guys were just zipping all over the place. It was unplayable. It was awesome. All right, but in any case, so maybe that's bad programming practice. But in general, from a standard computer, modern day computer programmer's perspective, we like this idea of having collections of statements that we can do in a certain order and not necessarily have them directly linked to each other. Makes decent sense, right? All right, so with that in mind, we're going to be creating a block statement. Now, we imagine that we might want to be able to display something inside of our block statement. Maybe we do a couple things and we display something from our environment, then we do something else and display something else. So we'll go ahead and write the display first. But that block statement is going to be a fairly handy thing for us, given that it's going to let us do multiple things at once, and it will then open the door for us to start having the ability to update a value of a variable inside of our code, inside of our language that we're inventing. All right, so we already have this done in parse, so let's go down to apply expression. And this guy is called a print expression, right? So we'll say print exp lc expression. If that's the case, then what we want to do is we want to ultimately, I think wasn't I messing with it down here? Don't we have something called display 8, to put it purple? Yeah, so we already have something called display that's built into, so we'll use display to ultimately do this. Actually, do we need to do it in display? I don't think that's going to hurt anything. Well, we'll roll with it for right now. So really, a print statement has a single expression associated with it, right? We had an extractor for that guy. So this is print expression to expression. That'll get us the expression. So as a result here, we want to go ahead and call apply expression. What expression? Our print expression to expression from our lambda calculus expression. And we want that to be executed inside of the current environment. So now we should be able to call our run program with this guy. We should get a purple 7 printed out. All of them were false. Did we not call it a print expression? This guy? What does that LC expression look like? I kind of recall us saying, let's leave an error here, so we'll fix it when we came back. So print expression says print, then we have list literal 7. So parse is giving us that as output. And we build that using a lit expression. Lit expression constructor gives us a list containing lit expression. Okay, yeah, so we haven't finished this yet. Parse expression is not done yet. So if we have a display, we want to create a print expression. So we have to look at our constructor for print expression. But now this guy right here, he's extracting that, but we actually need to call parse expression on that. So we're going to build a print expression on the parsed version of the expression that's going to be passed in there. This should give us a lit expression now. So print expression, and then we have a lit expression with the 7. Now we should be able to run this program, and we get our purple 7. All right, so we have a display now for what it's worth. You know, it just lets us show something. All right, so we want to think about our block expressions now, however we want them to represent them. So if we think about our language here, you know, in Java, we would say, you know, this, then a bunch of individual statements, then this. So this would be a lambda, well, what would we call it? A 0 or more code 3 expression, something like that. But what syntax do we want to have instead of curly braces? Curly braces feels very program-y. So obviously, we're probably going to have something that ultimately is a list. It's a list of coder expressions. Do we want to have any extra verbiage? I think in Scheme, the equivalent of this, there's a begin instruction. I think we can call it begin and do several things in a row. No, we haven't necessarily looked at. But do we have an idea for a syntax for this that maybe do in order? Something like that. I think maybe some older school verbiage might be something like batch, like run a batch of things. So let's go with do in order. Makes reasonable enough sense. All right, so we want to execute 0 or more instructions from this. Presumably, you probably wouldn't just have 0 instructions, but I don't think it's going to make any difference for us. So we have do in order, some 0 or more instructions. So let's go ahead and let's go through our process up here, where we put it after our print expression maybe. So define do in order exp to be a lambda that takes in a expression. Now this guy is going to take in a, really he's going to take in a list of expressions, right? List of expressions, good enough. So it's going to take in a list of expressions, and he's going to create a list out of print expression, I'm sorry, do in order expression, and my list of expressions. Now, realistically, this is going to be a list containing a symbol followed by its second element will be another list. Do we want it to be that, or do we want it to be flat? If we want it to be flat, how will we change this code so that it would make this thing flat? Where it would literally be a list with do in order expression, then expression, 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 without those things inside of a list. Because right now what it'll do is it'll create a list containing do in order exp, and then it'll have another list where maybe it has a, you know, a lit expression 7 and then another lit expression 8, just to make it simple. So it'll look like that right now. What if I want it to look like that? A list that contains the first thing and then everything else as a list. How can we accomplish that in our constructor here?
Yeah, just make a new list and do it then, right?
Yeah. So one thing we can do is we can say append list do in order exp and low expression. Like that. Can't we also just cons do in order exp onto low expression? Just adds this to the front of the list. It's kind of funny how we've gotten so used to using some of the more complex things that we don't use the simple things anymore. So we'll do that. Reasonable enough. So we'll cons the do in order expression onto that list of expressions to get me a flat list of the things that we want to do in order. But things are about to get a little interesting here. Well, I don't want to give away too much right now. All right, so do in order expression. That'll build this guy. Now, these guys right now are a list of expressions. It's going to be up to us to see how those expressions play out. Now, when we go down to our define do in order expression to list of expressions, this would be a lambda that takes in a do in order exp and boils down to the cooter of the do in order exp, the list of expressions, that's everything else. The first thing is the do in order word, the symbol do in order. So the list of expressions is just everything but that. Okay. So that's that piece of it. Then we have our predicates. Do in order exp, be a lambda that takes in a lambda calculus expression and boils down to, here, I'll just steal this. Do in order exp like that. Okay. Now, hopefully we're starting to see how easy it is to add stuff to our language as long as we keep going through these same steps of constructors and stuff like that. I think you're going to find that this do in order thing is actually going to be a little bit more complicated to implement for a reason that's going to reveal itself here in a minute. But still, just the idea of sitting here and saying, oh, I have this language. It doesn't know how to do this. I want to add that. Just being able to go through these sections and say, do this, do this, do this. That's kind of that abstraction thing we talked about before, where it might feel tedious, but it makes everything else look so much cleaner and work so much easier because your actual logic is housed inside of all these constructors and extractors and those types of things. And this goes right back to like software engineering classes where you look at stuff and you say, yeah, this seems kind of boring. I don't want to spend all this time planning. I just want to sit down and write the stuff. And you realize after you've maybe been in industry for a little bit that 90% of it's the planning. If you planned it right, the thing almost writes itself. I think I've maybe even referenced before, or Dr. Locklear might talk about it in the 370 class, that there's actually software engineering tools out there that if you use the tools to plan your design enough, it'll generate a whole bunch of the code for you. You just got to go in and maybe do a little touch-ups and stuff like that, or write some of the interesting algorithms, the more difficult stuff. Because that's at this point, most of you are juniors and seniors. At this point, you're good enough programmers that you can kind of tell the difference between that, the problems that are more complex and then the things that are just tedious. Like you feel like I have to sit here and for 15 minutes just writing if statements or something like that, where it's like something else could do this for me. This can be automated, that type of thing. All right, so we have our predicate for that guy, and then we need our, we already have our coder. Actually, we don't have our coder extractors for this. So we're going to need to do our, actually, will we need a, because we're calling it do in order, right? So define do in order expression to list of all the other ones. We kind of changed the name of it, the do in order thing. Or maybe internally we don't need to have the do in order. We just have a, although we do call it like a list expression. It's not going to hurt anything. It's fine. So do in order expression to list of expressions. This would be a lambda that'll take in a do in order expression. And ultimately returns the cooter of the do in order expression that will pass to the constructor for a do in order perspective, which just puts it right back into the form it used to be in. Yeah. Well, except parse is going to have to deal with each individual part of it. So I guess that's actually, yeah, this will actually be an interesting thing here in a second. In fact, I'm going to copy this. All right, so actually I'm gonna have to uncopy it here in a second because I'm gonna deal with this. So let's say that we are looking at a do in order. And that's what I decided my syntax would look like, right? Just do in order. Yeah, do in order. So let's say that the first part of it is do in order. Now, that means that following this should be a list of code expressions, right? So how do I implement? In fact, I'm going to kind of pause it right here for a second, and I'm going to give you a, well, I'll go ahead and save this. And let me, here, just so I don't forget for this from another class. I'm going to go ahead and push the current code up to Slack. I'm sorry, up to, where's our, oh, here it is, code language. I'm going to updated for display expressions. I'll go ahead and push to origin. So go ahead and take a couple of minutes and try to write this do in order for parse expression. And I'm going to give you an example of what this thing might look like. So we'll go ahead and say do in order, literal 7, literal 8, display literal 10. So we want parse expression to take in something as a do in order expression that has following it a list of expressions it should process. So the current code up on my GitHub is exactly what my code currently is. If you go to my GitHub. So take a couple minutes and attempt to, and actually here, I'll update it again. Since now you don't, now you have my example that I just wrote. All right, so now you have my example. So now try to write for parse expression, the do in order part. I think this will give you a little bit of a idea of the complexity we might run into in a minute with apply expression. All right, so let's take a look at this. So for parsing this, and that should have been plenty of time, I think, for everybody, but we'll do the apply expression as a group. So parse expression for this guy, if it's due in order, that's fine. What we need to do is we need to construct a due in order expression, and our constructor for that guy is up here, right? So here's our due in order expression. And this guy is expecting us to get past a list of expressions. So we will call due in order expression, and he wants us to pass it a list of expressions. Our list of expressions, we're going to use our extractor here to get our due in order expression to list of expressions. Okay, so now we have our list of expressions. What's the problem with this right now? This guy right here boils down to a list of unparsed expressions. I need to parse those expressions. How do I parse those expressions? Well, you could write a helper function, or you could put something in here that goes through everything in the list, right? So we could create a helper, define, let's call this apply parse expression to list. And this is a lambda that takes in a list of code expressions, right? And then what we'll do is we'll have our old friendly pattern. So if null, this dude, boil down to the empty list, else, I'll put it right there, else cons parse expression on the car of the list of these guys onto whatever's returned by this function on the coder of this guy. Like that. Okay, any better way we can do it? Could use map. Could use map. So, we'll go ahead and write it this way real quick. So what we'll do is we'll do, where am I at? Where's my parse expression? Do in order this guy. Okay, so that's one way we could handle this. And was defined previously, you cannot redefine it. Where did I define it previously? Do in order expression to list of expression. This is my coder. Yeah, remember I said earlier that we name things the same as before. So let's just call this guy do in order to list of expressions. All right, so there's our one version of this, right? Using our helper function, or we can call, we can map parse expression across that list. So this is a expression that takes a single parameter and we want to apply it to every element of this list. So this will give us our same output without our helper function. And as you might imagine, as our interpreter gets more and more complex, being able, I mean, that's a good use of map right there, right? You know, it's perfect use of map. We happen to have something we want to apply to every element, takes one parameter. As much crap as we have inside of this interpreter already, we probably don't want to have any extra helper functions laying around that we don't need. There's a point where you just can't manage that stuff anymore. So this is probably a situation where map will benefit us. So we'll stick with the map version of that. So we're going to create, here's our constructor for do an order expression. We're going to use map to map this function called parse expression, which we're currently inside of. So I'm going to map that expression to all of the code expressions inside of this list. All right, questions about that? All right, so then ultimately we're left with this, you know, ready to apply expression list of expressions that we want to do in order. And actually, I'm going to make a small little change here. I'm going to call this guy a var. Oh, what do we call it? Remember? What do you call it? Find. What do we call it? Get value. And this guy should still work fine. Oh, yeah. Did I write my function wrong? I'm displaying. Isn't that how we, oh, is it lowercase get value? I just copied it for my stuff up there. Yeah, lowercase get value. All right. So we want to start thinking about apply expression here. I want to look real quick. Did I put something else in? Order. All right, we don't know how to remember something yet. Well, this will still work out okay. I think we can all agree. In fact, I'll even make it up for right now. I'm going to say, remember A13, something like that. We definitely want to be able to remember variables, update values inside of our environment, right? Okay, so I think we can all agree for at least a minute, even though we haven't written this yet, that we get what this means. Update a variable named A to 13, or create a new variable named A13, something like that. Any way you cut it, this guy will have a bearing on this guy. We say do in order, but we might be, you know, if when we do these in order, and we've already gotten our answer down here, we want to call apply expression to this guy. And we want to call apply expression to this guy. We want to call apply expression to this guy. We might be tempted to, even though apply expression can't be mapped because it has two, it can't be directly mapped because it takes two parameters, but we could probably fake it. We can write another expression, another function that takes in a list that has the two elements in it and then parses them out and calls apply expression with it. So like, the super mapper, apply expression mapper that takes in a list, a two list, and then calls apply expression on the car and the catter with it, and you could pull it off. So you might be tempted to effectively to map apply expression across this list of expressions. The problem with that is if one of these expressions, for example, my remember one here that we haven't invented yet, but if one of my expressions has a side effect on the environment that this guy should be applied within. Okay, so the idea here is that I can't apply this expression until after I've finished applying this expression, because applying this expression may have had an impact on my environment. And my apply expression runs by applying a particular expression in whatever the current environment is. So I can't just go through and map them all across. So let's look at what we can't do, and then we'll talk through that. So I can come in here and we're going to do this as a, what's my predicate for it? Do an order expression question marky thingy. This guy. All right, so if it's one of those dudes, we might want to, and here we'll again, instead of having a helper, actually, this would be an interesting question. If I wanted to effectively map apply expression across need to use my extractor here. If I effectively wanted to do that, I wanted to map apply expression across this list of expressions, knowing that apply expression takes both an expression, so one of these, as well as an environment. Try to write the code in line here. Can't use a helper function. Write the code in line that will allow me to effectively map apply expression across this list. And you can assume that all of those expressions are going to be executed with the same environment, the same env. So we're not solving the problem yet that I've been talking about, where one expression might modify the environment of a previous expression, because our language doesn't know how to do that yet. All I'm saying is that technically map only works with functions that take one parameter. How could you hack this? Maybe with a lambda, hint, hint. How could you hack this to use map to effectively call apply expression across every element of this list with the current environment? All right, so take a couple minutes and see if you can figure that out before we just write it. No helper function, got to write got to embed a lambda in there that does the magic. Mike Myers at the window. All right, so let's take a look at this. So map takes in a function that has one parameter that we're going to map across every element of a list. So the function is going to be a lambda that takes in a single parameter, each element of the list. I mean, if you want to call this, you could say an expression. What are these guys? It's actually, I'm just going to call it X here. So that guy, and what's it going to do with it? We're going to call apply expression on X in the current environment. That will call apply expression on all those guys in the current environment, producing a list with the result of each of those. So here's my lambda. What does this function do? It's going to get applied to everything in this list. So each expression will come in here as a parameter. What will I do with that parameter? I'll call apply expression on that parameter with the current environment. Current environment is not bound here, but it's bound here.
Does that need to be like second, since the order is when you calculate expression in that environment? Like, is it-
Oh, I don't remember. No, that's right. X is the lambda calculus expression.
Right, but that whole map expression, should that come after if you would order expression, list expression?
No, because map says map a function across a list. So this is my list of expressions, right? That's what this guy will boil down to, is a list of expressions. So that's the list I'm applying a function to. What function am I mapping? I'm mapping this function. The function that takes in as X each individual element of this list and calls apply expression on it, on that function, or on that lambda calculus expression with the current environment. So this is the single parameter function that I can pass through here. And I'm hard coding in the environment. So it does only take one parameter, the parameter being this single expression. And then I'm calling apply expression with that single expression and then my environment that I already have access to. That'll allow me to use map in this case. So we come down here to this guy. Here's my parse expression for my do in order. I'll just steal this. So what we should get here is a list containing a, well, that will break, right? We don't have a remember yet. We should have here is a list containing a 7, containing an 8, technically containing, actually, I wonder what's going to happen with the display on the get value A, because display doesn't boil down to a value. It puts something on the screen. I don't know if I'm going to get a purple 6 out of this, or if I'll see a purple 6 on the screen, but I might get a null value in my list. The result of calling display. Like, what is display is a function. That function does something. This goes back to like CSC470, right? This is a function that does something but doesn't return a value. I expect it to put something on the screen, but it doesn't actually return a value to me, where I'm going to be adding the value it returns to my list, which I don't know if it's going to be like a false or a null, or, well, I guess let's find out. You know, in Python, it would be none. is what a function that doesn't return a value gives you. Java, we can't, if you try to use it, it's to scream at you and say, this guy doesn't return anything. Yeah, void. So we got our 6. So it did it. You know, it performed its action. So we got our 7, we got our 8, and then we got the value that display boiled down to, which is a nothing value, something like that. Yeah, kind of an interesting thing though.
And is that just because it applies this
Well, no, it's because display is a function that does something but doesn't return anything. You know, so if I say 6, it just iterates 6 to the screen. But if I say display 6, is it going to look different to me? Maybe it's this. What if I call display on display? Display on display of 6. I'm guessing this is going to give me an error because display requires something to work. I'm giving it nothing. Display 6 there puts a 6 on the screen, but doesn't boil down to anything. It's a nothingness. It's either going to fail because it requires some input, or since everything seems to be a first-class value in scheme, I'm guessing void is the same thing. Void counts as a value, and what it'll do is it'll display void in purple. So this could give me a 6 in purple followed by a void in purple, or it could give me a 6 in purple and an error. I don't think it'll give me a error ahead of that because it's an interpreted language, and usually that just goes in order. Oh, well, I just didn't even run it. I ran. Yeah, 6 in void. So it's a first class value. But we see there that the result of this, what does that do? That displays something on the screen and then boils down to void, boils down to nothing. All right, that makes some sense. Okay, so now the next thing we want to do is, so right now this sort of kind of works for what we want to do until we break our language here. That is to say, we're going to go ahead and we're going to add a remember instruction. So we remember, you know, like A13, something like that. And what this should do is it should update our environment. Now, this is going to start putting us into a kind of an uncomfortable area of, right now we don't have scopes, right? We have an extend env. So what we could do for right now is we kind of have to make a decision. What I might suggest is, because we haven't started talking about scopes yet, whenever we remember something, we just treat it as it's a brand new variable, rather than going and updating an existing variable. Okay, which would mean that the result of a remember would be to extend the environment. Okay, for right now, because we haven't talked about scopes yet. Because if we're inside of a scope, when we start dealing with functions and we update something, or maybe we even change it, maybe we have a remember and then we also have an update, something like that. But this at least gets us down the path of being forced to solve this do an order thing better than what we're doing right now. Because we're getting away with a lot right now because we're not allowing, each of these is being executed in the identical environment. It just so happens that our language currently doesn't support changing the environment along the way, but it will in a minute or in a couple of minutes. And then we have to be more careful about this, because then we can't say, well, they're all going to get done in the same environment. Now we have to say, well, we're going to do this guy in the current environment, and then this guy in the resulting environment, and then this guy in the resulting environment of that, so on and so forth. So it becomes a more complicated problem. All right, so we're going to have a remember expression. So we'll have our constructors here. So we'll remember EXP. Now we don't have to call it a remember here, but I kind of like the remember. So we can kind of do the same thing we did in do in order. Actually, we could do it as a create var expression. That might remind us what we're actually doing. Because this idea of remembering something, we're going to decide to treat that as creating a variable, not updating an existing one. It's going to create a new one. So let's call it create var expression. And this will be a lambda that's going to take in a var name and a var value. And it's going to create a list out of a create var expression, var name, var val. All right, then our extractors define create var expression to var name is a lambda that takes a create var expression and it returns the catter of create var expression. Define create var expression to var val. This would be a lambda that takes in a create var expression and it'll return the car of the coulter of create var expression, like that. All right, so this is our extractor for those two pieces of information. So again, this is that same thing. This is kind of tedious, but makes our life a lot easier in a few minutes. All right, and those are the only two things we would need to extract from that. Go down to our predicates here. Define create var expression to be a lambda that's going to take a lambda calculus expression. Oh, yeah. And it returns whether or not the car is equal to, well, whether the type is equal to a create var expression. And we have our code extractors. So we'll have a define remember expression to var name to be a lambda that's going to take in a remember expression. And it's going to boil down to the catter of our remember expression. And then we'll have extractor for var val, CADDR. And that's going to be used by our parse expression. So we parse code into our constructors, and then we apply those expressions in our environment. All right, so this is going to be our remember. So we can go ahead and put it wherever we want in here. We're going to do this equal car. Remember EXP. So if I'm looking at a remember EXP, then what am I going to do? I'm going to build create var expression. And create var expression is going to require me to give it a name and a the value. Now the value is probably another expression, right? But the name is just a symbol. So I don't need to call parse expression on the name. So I'll create this guy, and I'm going to go ahead and use my extractor. And this is going to be my remember expression to name. All right, so that's my symbol for the variable name. I don't need to parse that. But then I'm going to call parse expression on var val of this guy, because potentially that's a lit expression or another var expression. I might be remembering A is equal to B, something like that. All right. So that should give me my parse expression for that guy. So let's go down here to parse expression on this, and we put a remember A13 in there. I'm going to remove the run program thing for a second. Questions were false. Let me make sure I wrote it right. Remember, this is not A. This should be a literal 13. Remember A to be equal to a literal 13. Oh, it's a remember expression. I want it to be called remember. That's why they were all false. Okay, so here is my do in order. Here's my create var expression. A is equal to a lit expression 13. Okay, so it looks like this is parsing it correctly now. So for our homework, update apply expression to work for remember. Actually, we want to call it, what did I call it? Create var expressions by having it extend the current environment with a new name value pair. Then update apply expression for do in order to execute each, well, to call apply expression on each element of the list of expressions using the resulting environment from the previous call to apply expression. What I mean by that is if I say do in order remember A, well, here, we're going to go like a T is equal to literal 3. And then I say, what do I call it, display? Then I say display get val or get value T I should first remember that t is equal to 3, and then I should display the 3. Because if I'm doing it the way I'm doing it right now, where my environment does not have a t in it, it's going to say that guy's not found. Make sense what I'm saying? All right, so you're going to have to fix. We already wrote a bad version of do in order. That does not take into consideration the chance that the environment has changed after each expression. Okay? So you have the current version of my code that has finished parse for remember, but hasn't written apply expression for remember, but that shouldn't be that big a deal. You're just going to return a new environment, okay, which is great, because you're going to need to use that new environment in the other guy. So that's going to be the trickier part of the assignment, is the how do you fix your do in order so that you can keep track of the environment you just had as you're going through it. Okay? Questions, comments, concerns, bribes? All right, I will see everybody on Tuesday. Well, ever since I've been saying that phrase, jokingly, yes. Previous to saying that phrase, I would say the answer is probably not here, but my previous school, Western Illinois University, I would say probably. Like, it didn't come off as a joke. Like, it was at least a question whether it was a joke. Yes. Sometimes people get desperate. They're only hurting themselves. I mean, I'll take the money. Actually, it's usually food. Food's far easier, right? Like money, you really can't treat money like a bribe. But, you know, they bring bacon to the final exam. You got to eat. And that's actually just poor form, because it's not like I'm grading the final exam while they're taking it. You really want to make sure the bacon's available to put me in a good mood while I'm grading it. So, yeah, if you're going to bribe me, do it right. It's kind of the